Hello, testing. Hello, testing. Hello, testing.
Hello, testing. Hello, everyone. Good morning, and a very warm welcome to the first live session of the program. I hope I'm audible. Just say yes in the chat box. Okay, that's great. I hope there is no echo and my audio is absolutely clear. Okay, clear. Perfect. Thank you so much, everyone. I'm Ashish Nagar, and I'm the head of the learning experience team at Upgrad. And since this is our first live session together, I'm super excited to welcome all of you. We will take just a quick minute as many more learners are joining in. Meanwhile, I would love to hear from you. Please drop a message in the chat box and let us know from which city you are joining. Okay, Pune, Chennai, Bangalore, Pune, Hyderabad, Ahmedabad. Great, someone has joined from Ahmedabad. Uh, by the way, I have also joined from Ahmedabad. Professors are at IIT Kharagpur. And some of our team members, they have also joined from Mumbai, Bangalore, okay, Hyderabad, Delhi, Indore, oh, Sydney, great, Delhi, Switzerland, Bangalore, Florida, Indore, oh, 5:30 at London, basically from Chennai, okay, Hyderabad, Pune, great, we have learners across the world, Vishakhapatnam, Noida, Bangalore, Bhubaneswar, Raipur, Pune. I can see a lot of learners have joined from Mumbai, Pune, Bangalore, Nagpur, okay, Chennai, Pune, Hyderabad, Gurgaon. Okay, that's really great. Once again, a very warm welcome, everyone. Uh, before we start our first live session today, I would want to cover a few important points to ensure a seamless learning experience. So I'll just need your 1 minute of attention, and then I will be covering few important points. Ankit, if you can move to the next slide, please. Yeah, so before we begin with our first live session, some of the important points. Uh, Please use the Q&A section for all your academic queries. Our teaching assistants are available there to address all your academic queries. While during the session, professor will also address some of your queries during some Q&A time. However, teaching assistants will ensure that they will be responding to all your queries in the Q&A section. We have chat section also enabled for all of you. Chat section is there for all non-academic queries. In case if you want to highlight any audio video related concern, or if you have any generic query, please feel free to drop it in the chat section. I would request once again, there are two options. One is Q&A and other one is chat option. Please use Q&A for all academic queries and chat section for all non-academic queries. The next important point is that this session is being recorded and that recording will be shared with you. So focus on understanding rather than note taking. Of course, you feel free to take note, please. But the point to highlight here is that this session recording will be shared with you. The next important point is that all the queries which you will be raising in the Q&A section, if academic and if non-academic, and then in the chat section, they will be addressed promptly. And if there are further academic queries, our TAs will be available after this session as well. So the session timing is from 10 a.m. till 1 p.m. However, TAs will be available after 1 p.m. as well to ensure that all your queries are addressed. Now, after this session recording will be available on the platform within next 24 to 48 hours. You please watch that recording, and in that case, if still you have some more academic queries, you know the discussion forum. I'm sure you all are familiar with discussion forum. If you have not explored that, I request you to explore it today after this session. It is very easy to use, and you can put all your academic queries over there. You can interact with your peers there. They can also respond to your query. And then teaching assistant will also respond to your queries within 48 to 72 working hours. So use that platform. It's a very good, very easy to use. Other than that, for all non-academic queries, you please feel free to write to studentsupport@upgrad.com. And Your program coordinator, Tushar Bagul, and our team is there to respond to you promptly. Okay, now I'm moving to the most important and exciting part of today's session. And it's my pleasure to introduce our esteemed speaker, Professor Niloy Ganguly. Niloy sir is a professor, higher administrative grade since August 2020, and he serves as the head of the Department of Computer Science and Engineering at IIT Kharagpur since 2024. He is a fellow of the Indian Academy of Engineering and the Surojit and Sanchayata Chatterjee Chair Professor. He has also spent 2 years as a research scientist in Technical University Dresden before joining IIT Kharagpur in 2005, and he has risen to the rank of professor in 2014. He has done his BTech from IIT Kharagpur and his PhD from IIST Shivpur. His research interests lie primarily in social computing, machine learning, natural language processing, and network science. He has published in 80 journals and 200 conferences, several of which are in reputed international venues. Professor Ganguly's work has been recognized through awards by NSF, Cisco, NetApp, Samsung, and Yahoo. He has received prestigious research grants and projects, notably from Data Transparency Lab, Imprint, ITRA, Intel, HPE, Adobe, Microsoft Research, Accenture, BEL, and TCS. He has guided 25 PhD and 9 MS students during this tenure. He is the founding member of the Complex Network Research Group, comprising faculty members, research scholars, and the student affiliated with the department. There are many more achievements to highlight, but in the interest of time, I will pause here. With that, let's get started and dive into today's session. Over to you, Professor Niloy.
Should Yeah. Share the screen? Yeah, welcome. I guess it's unmuted. Can you hear me? Can you hear me? Yes. Okay. Great. So let us share the slides. Yeah. Okay. So welcome to this course, and it's a great pleasure and honor for me to start this course, and I hope all of you would enjoy uh, with us. Yeah. No, hold on. Sorry. Huh? Continue. Okay. So now that we are all familiar with artificial intelligence, just this session would tell you about the genesis, how it started and how it progressed. And we'll come to the cusp of deep learning in this session. Just give me a second. Let me just close. I think something needs to be done to close this. Huh? Anyway. Okay. So I guess the birth of AI came in the 1956 Dartmouth conference, and stalwarts, some of them stalwarts, if you see McCarthy, you may be knowing some of their names, McCarthy, then Minsky, okay, Shannon. These were the stalwarts who came together and first gave the name AI, artificial intelligence, and that the name AI was coined in 1956 Dartmouth conference. And what was the issue? To proceed on the basis of conjecture that every aspect of learning or other feature of intelligence can in principle be so precisely described that the machine can be able to simulate it. So this is the point which the founding fathers of AI thought, that learning or any features of intelligence can be very precisely and crisply described, and a machine would be able to simulate it. So with this, the journey started, and these are some of the major milestones. If you see that the Alan Turing proposed the Turing test in 1950, even before the AI coining was there. In 1956, we had the Artificial Intelligence Conference. Okay, and in 1959, the term machine learning was coined, and then we had the first chatbot Eliza in 19 as way back in 1966. In 1975, we saw that AI, the expert systems begin to come, and expert systems in medicine begin to come, and then several other things begin to come. But we see that this is an era, we'll later see that this is an era where the surge of AI was seen. The surge of AI was seen. And then there was a dump. And after that, from 1979 to 1997, we saw various things going on. But then again AI began to become more popular. And one of the important thing which happened, which made AI extremely popular and also shook people during that time, was Kasparov was beaten by a computer. So just now, looking back 30 years, for 30 years, it seems very natural, but at that point, it was thought to be a very, very important milestone, because there was an understanding within humans, and means I have gone through this period. There was an understanding within humans that playing good chess is one of the last bastion of human intelligence. So that got broken, and people also understood that there are many things intelligent than just playing chess. And then we begin to see the machine learning era going from strides to strides. And in 1970 to 2017, we begin to see the deep learning and generative AI starting. So this is what it is. I know many of you may be knowing, but just for completion's sake, we talk about the Turing test. What is the Turing test? A human judge communicates with a human and a machine over text only channel. So a human judge is sitting and it is communicating with a machine and also a human. Okay. And what is happening? Both humans and machine try to act like human, and judge tries to tell which is which. So whether the judge can differentiate that this is spoken by a human and this is not spoken by human. Okay. So like judge asks, the book was written by Jane Austen, while the robot says Jane Austen wrote the book, which may be a little bit not so human like. Okay. So this is what you try to see, that the can judge tell which is human. If the judge fails to differentiate, AI passes the Turing test. And there has been numerous variants. The ELIZA program started in 1966. From 1966, people are trying. And then you have all sorts of AI chatbots going on in this present era. And what we know for ourselves, that differentiating between AI and human is increasingly becoming difficult. So that way, the Turing test, AI is passing more and more easy Turing test, and it has to be real. If you have to fail AI, you have to have really difficult Turing test. So this brings us to what is artificial intelligence. So we have thinking humanly and rationally. So there are two things: thinking humanly and rationally. So all of us know thinking humanly and rationally are not two things. There may be a lot of overlap, but not that all the time humans are rational, etc. Okay. So automation of activities we associate with human thinking. This is what Bellman in 1978 proposed. Okay. Like decision making, problem solving, learning. So interestingly, that when we were talking about human thinking, we are talking about decision making, problem solving, learning, and that is what we want AI to simulate. Means think about in 1978, Bellman has no idea that AI would also begin to write poetry, AI will also begin to write good prose. Okay. So he has never talked about creativity that way. He has never talked about creativity. Okay. And it was too far for somebody to think in 1978 about that. So this is about study of mental faculties through computational model. And what is needed is systems that think like humans and systems that think rationally. Okay, so and these two are actually very difficult. Means the first one is more difficult than the second one. So what is a engineer's take? What is the engineer's take? Engineer's take is systems that act like humans. I'm not caring about how the system is thinking. I'm telling the systems that act like human, system that act rationally, achieve best outcome. And so there we have four quadrants. One is thinking, one is acting, and one is human and rational. So it is fine. Modern AI primarily thinking of acting rationally. Okay, so example, AlphaGo act rationally, not necessarily like a human player. Okay, so just again, for completion's sake, we talk about good old AI days, and good old AI days were in the late 1970s and then in the 80s. Okay, so there were three basic pillars, and these pillars are, if you know, these pillars are even coming back now in various different ways. One is logic, like formal symbolic reasoning using propositions, predicate and inference rules. Rules like if then productions rules that encode expert knowledge for automated inference. And then you have semantic graphs, graph based representation of concepts and relationship between them. So these are the three basic blocks on which things developed. So let me just go through the logic part of a few. All people who are graduating are happy. So for all graduating X, happy X. All people, all happy people smile. So happy X implies smiling X. Someone is graduating, so there exists a X where graduating is X. So from that, the question can come, is someone smiling? And you can derive from this propositional logic that there exists a X where smiling X. Okay. So this is how you begin to derive logically. This is actually multiple steps of various statements from which you derive the predicate logics, and you can very efficiently, there has been an elaborate math on predicate logic, you can elaborately, very efficiently derive the outcome. The other is rule-based system. So if gas in engine and does not start, say rule 1 is if gas in engine and does not start. Okay. And second one is then problem spark. And second one is if gas in tank and gas in carb, then gas in engine. Okay. So now, if these are the two rules which are there, now you see gas in tank is true and gas in carb is true. Okay. And problem is, so, but does not start is also true. Then what has happened? So gas in carb and gas in tank and gas in carb means gas is in engine. So now I go to rule 1. So gas is in engine and does not start. That means you can derive that the problem is in spark. Okay. So this is how rule-based systems helped to navigate through complicated problems and give you solutions automatically. The third basic major block was the semantic net, while a graph where nodes represent concepts, a node represents concepts and edges represents relationships between them. Like Nelly is an elephant, lives in Africa. Elephant is an animal has head. That means Nelly has head. Okay. So this way you can do, and semantic nets, interestingly, is still there in forms of some, we now call it knowledge graphs, and these are also used as side informations to our deep learning and generative models present day also. But these were not enough, and this led to build up expert systems where there were rule engine, there were knowledge base, and there was a user interface. So sample input, the knowledge base would work, and they would produce advice. So this is how expert systems became very, very popular in the 80s. And there was big projects on building expert system. However, it hit the wall. Key challenges that caused first AI winter when funding dried up and progress stalled, because there was ambiguity. See, real life has lot of ambiguity. So like this is a classic example. Highly funded translation program, Russian to English, were good at syntactic manipulation but failed at semantic disambiguation. So this is, I think this is a cartoon, but it's too good to even think that it was true. But this I have seen for last 30 years, so I believe this is true. The spirit is willing, but the flesh is weak. Okay, so and this is a translation of the vodka is good, but the meat is rotten. Okay, so this is a literal translation which happens when there is a system which is not geared towards tackling ambiguity. Okay, and this ambiguity is there everywhere. Ambiguity is there in way I am teaching. There are various ways you can interpret it. Even now, when I'm speaking, there is ambiguity in my talks, and you have to get a system has to understand that ambiguity and act accordingly. So that's why there was a scalability. Early AI examples were very small and narrowly scoped. Program could not scale up to handle bigger or more complex real world instances. So this was a issue which happened. And the knowledge representation scheme used like rules, semantic nets, were too brittle and could not handle uncertainty, ambiguity, or common sense. As you know, common sense is a very uncommon thing. So common sense, it was not able to handle. So this brought in what we call the AI winters. And this is how it goes. So there was this good old AI, okay, good old AI, and where it was mostly in the walls of MIT, CMU, Stanford, the big universities and big people, McCarthy, Minsky, who gave basic idea like heuristic search, etc. But that slowly didn't go to some practical application, and we had the first winter. But then in the 1970s, it began to boom like anything, and we saw all sorts of expert system coming out, and important conferences like AAAI. Many of you may be knowing that AAAI is still there, and AAAI was a huge conference that time in the 80s. It became a huge conference. All important people from all universities began to flock in AAAI. But then there was this winter, and then again we had this boom, and this boom has come through the advent of deep learning and machine learning. Okay. So what happened? What happened that we saw the machine learning part. Okay, what happened? We saw the machine learning part. And so data. So data is the new oil. We call data is the new oil, but in this present context, I am not so sure whether this is a right way of telling it or not. But data is the new oil. And we begin to see, after internet came, we begin to see a huge burst of data. So if you even remember, if you think of parents, grandparents, how many numbers of photo they have. They may be having in their entire life 5 photos, 10 photos. Okay. But now even in 1 week, you are having 5 to 10 photos. Okay. Good photos. Okay. So we cannot even imagine how data bursts. And I have some numbers. These are not so important that you have like 333 billion plus emails sent per day, 8.5 billion Google search. Okay, the global data sphere is like 175 zeta. I don't know how much is this even zettabyte. Okay, and 90% of world data is created. So this is very, very interesting. See, 90% of the world's data is created in last 2 years, and world has existed, at least the human civilization has existed for 10,000 years. At least a conservative estimate is the human civilization has existed for last 10,000 years. One point I would like to say is that although there is a lot of data, many of these data are not labeled, and only 1%, I think 1% is still a good estimate. I think even less than 1% data is labeled. And data can be categorical, ordinal, continuous, these various sorts of data we begin to see. And I have some small things which is written about that. You have email sent, crypto purchase, text sent, Google search, Snap shared on Snapchat. So I can go on forever, and you can see that hours spent since Zoom meeting. Already we have spent maybe 15-20 minutes. It adds to this amount of hours per minute which is spent on Zooms. Okay. So, yeah, because there are several charts, and we see that things are moving at dizzying pace. It is moving at dizzying pace. So we saw that even now, even pre-2020 begins to look like prehistoric. Even pre-2020 begins to look prehistoric, when we see this rise of AI, the large language models, which really begin to come with the advent of so much data, compute power, etc., everything coming together. And we have this GPT-3, first open LLM, explosion of foundation models, multimodal and larger context, and frontier models, and rapid innovations around agents, etc. Okay, so this is what our course will try to capture and try to. We'll also learn with you. It's not that you will also learn. We'll also learn with you, and we'll also do the journey of AI with you. So again, Tom Mitchell, you may be knowing, Tom Mitchell is one of the pioneers in AI. So a computer program, so I'm just defining machine learning. A computer program is set to learn from experience. A computer program is set to learn from experience C with respect to some task T and some performance measure T. So experience C, task, and some performance measure. And if its performance on T as measured by P improves with experience C, then this is what is called machine learning. Okay, so you are continuously improving as you have more and more experience. And this is what also happens with us, means we flat out after some days, but this also may happen with machine, that with more and more experience, you get more and more idea and your performance improves. Okay, and here experience, we can think experience as something which we call as data. Okay, so how is machine learning divided? So there are two major things. That is, one is supervised learning, okay, where there are labeled data, model, and there is a prediction. And there is unsupervised learning, okay, where there is unlabeled data, model, and you try to have some clusters. I'm assuming many of you know this. I will go through this quickly, but again, these are very basics. This will come back again and again throughout the 100 hours where we are together. Okay, and then we have the reinforcement learning, where there is an environment and agents interact with the environments, and accordingly agent gets rewards or penalties, and with reward, if it improves, it gets rewards. If it doesn't improve, it gets penalties, and accordingly agents adjust and learn about the environment. So it is a continual learning is a different concept, but it is learning continuously. Okay, this is how reinforcement learning works. So let us talk about the course supervised learning paradigm. Okay, let us talk about the course supervised learning paradigm. So every learning paradigm, again, if you remember Tom Mitchell's things, that you have to have experience. This is what Tom Mitchell has told. So experience means, how will you have experience? If you have training. So that's why during training you have data, and training data has some input out. Okay, what has training data have? So you have a training data here where there is a picture of a cat and there is a label of a cat. So there are two things, the picture and a label. So, and this you can think as X and this you can think as Y. Okay, this you can think as Y. Okay, you have picture and you have label. So, you learn a mapping between this picture and the label. This is what is your task. You are learning a mapping of a function X and Y. So here, what is the task? Classification between cat and dog. This is a task, classification between cat and dog, but there can be also regression work. So you have to predict that what will be the house price after 5 years, or how will the share market behave after, at the end of the day. Okay. So this is how things are there, and you have train and test split to evaluate generalization. I'm coming to the term generalization in a bit. And but the big problem is, the key challenge is to get labeled data. So what is labeled data? Again, you have to have a lot of pictures, I'm drawing bad, very bad, but I'm drawing a lot of pictures of cat where it is labeled as cat. Okay. You have to have a lot of pictures of cat which is labeled as cat. And this is again not easily available. And if you have to make it available, perhaps you have to pay and get it annotated. Okay. So this is how, now let us talk in a little more detail, that you divide the data set into train and test. Okay. So there is a training set and there is a testing set. So what is happening? You are gaining these experiences. Okay. You can think you are gaining these experiences. Fine. You are gaining these experiences and you are, just let me write in a little bit, experiences. And from this experience, you have to say whether you can really understand the unknown. Okay. So which is not there in your, which you have not encountered in your experience. That's why I am telling it unknown. But similar type of things you have experienced in your unknown, in your experience. So then this is an interesting point. See, then when we are doing this train and test, there is a requirement that this should be disjoint. Okay. There is a requirement that this should be disjoint. The machine should not see something which not see something in the test data set. Then what will happen if somebody sees something in the test data set? Then it will be some sort of memorization. Means that may be also good. I'm not telling memorization is bad, but memorization doesn't lead to generalization. Like, I will tell you that if you say you are learning English, now you learn, and you have to give exams. You have to give exams in English language and you have to write an essay. And now you have memorized one essay, that my hero essay you have memorized and gone to exam. And if my hero comes, you are writing super. But if it comes that a day in the bazaar, then you are not being able to generalize. So it is important that experience is not about memorization. Experience is about generalization. If you have written at home, if you have written a essay on my hero, that writing should be done in such a way that if in your exam one day in the bazaar comes, you would be able to write it well. Okay. So this is very, very important from machine learning point of view, the generalization concept. So now what happens in this supervised learning? See, you have the raw data, then you have the feature extractor, and you have the ML model. You have the raw data, you have the feature extractor, then you have the ML model, and from this ML model, the learned parameters means the training of the ML models. So you have cat and dog, but cat and dog per se would not help. You need some sort of feature extractor. So you extract the facial features, and dog is more pointed while cat is more flat. Okay, this helps us to differentiate, and you can build up some machine learning model. I'm not going into this. I hope all of you know this, or if you don't know this, please go and study that there are decision tree, linear regression, what sort of support vector machine, etc., etc. And this machine learning models learn the parameters using this facial features. So this is the training phase. And once you have the training phase, you have the testing phase, or also we call this the inference phase. Okay. We call this the inference phase. Inference. Okay. So what happens in the test data? You have some pictures, it may be a dog or a cat, and then you again have the feature extractor. You have the feature extractor, and then these models which are now trained and have their learned parameters fixed, they have their learned parameters fixed. They classify, they classify and they classify and put it as dog or cat. Okay, they classify and put it as dog or cat. So either it becomes a dog or it becomes a cat. I guess this is very, very simple and very elementary, and all of you are been able to catch it and get it. So now I'll just dive a little bit into a little bit of coding thing. So how do we code these things? Okay, so we use scikit-learn. Means there are many other tools, but we use scikit-learn is one of the most popular tools, and I would request you to go through the scikit-learn documentation. Okay, and the matplotlib, which helps you to do this plottings, and numpy, which helps you to do these calculations. And if you have your machines around, you can install this scikit-learn, numpy, matplotlib in your package, in your machines. Okay, if you cannot do it now, it is fine. Just go back at home. Means when you finish, just do this. Okay, and just to give you an idea, that scikit-learn has lots of packages like supervised learning. In supervised learning, there are two tasks: classification and regression, and you have support vector machine, decision tree, random forest, gradient boosting, and you have in regression you have logistic and linear regressions and KNN sort of things. Okay, while you have the pre-processing and pipeline. So pre-processing is something which is very underrated, but you have to pre-process data, put it in proper form. That is what scikit-learn does. It also helps in unsupervised learning like clustering, etc., etc. There are various clustering algorithms like k-means, dbscan, PCA, etc. And then there are key design principles which we will talk, some things like consistent fit, transform. Okay, This side of things it does. And also it helps in model selection, that what type of loss function you will have and what type of evaluation you will have. Okay. And finally, it has some ecosystem and use case, like it actually, scikit-learn actually works with NumPy and matplotlib, which we also use in this example. So what is NumPy doing? Again, you can go quickly and see it is doing various setups, but it has an array creation. Okay, it does maths and aggregation. It does indexing and slicing. Okay, and this sort of all sorts of mathematical operations, NumPy is a very good tool. Okay, it has all sorts of functions which you can easily use. And if some of you are working with C or legacy languages, which are very good languages, most of the works which we have to do explicitly, NumPy does it in one shot. Okay. And then you have this matplotlib, where you can do very, very good plottings like basic plots, figure and axis, styling and customization. You can have layouts, okay, and advanced plot types like contour, heat map, 3D generation, etc. All sorts of things. Means in short, all sorts of things can be done through matplotlib. Okay. So with this, let me just go through one small problem. Okay, this is a supervised learning using scikit-learn. Okay, so breast cancer prediction is a binary classification problem where the goal is to determine whether a tumor is malignant or benign. Okay. So cancerous or non-cancerous based on measurable characteristics of cell nuclei obtained from medical imaging of biopsies. Okay, and this is what you can surely do using scikit-learn. So you first load the data set. Okay, you first load the data set. Okay, for scikit-learn data set improved from load cancer. Then you load the data set to the data, means to the data mm, mm, data mm, data name data structure, which has like data name structure which has the target name. Okay, so you can have the list target names, so which is the class names, and there may be two target names like malignant and benign. And then you have the data part and you have the target part. Okay, so now data has two structures. One is the data part, which is the exact data, and the target is the label part. Okay, I think this is clear. So once you do this, you can have some scikit-learn model selection. You can select some model, okay, and import train test split. So you are actually splitting the train and test. So split the data sets into training and tested. Split the data set into train, learning patterns, and test, evaluate performance. And then you have some sort of things which prevents overfit. I'm not going into this. I'll go to this in later thing. But you have a standard split of 80-20. See here, test size is 0.2. So if you have a data set something like this, you split it randomly, and 20% is for test, while 80% is for train. So this is how you are using supervised learning using scikit. So you have a train test split and you train the model. Okay. So you have to train the model, and then there are some other things which you have to do. Like if you are having you can have standard scalar. So this is again not so important at this point, but you instantiate scalar property and you fit transform. Okay, the train is fit transform and scalar transform. What is it doing? That this is scale sensitive, so the data is scale sensitive. Features should be normalized, improves convergence and performance. So what is happening? You fit transform or scalar transform, it scales the data. So data may be like within a range of 0 to 50, but you are scaling everything to 0 to 1. So data range, this is a simple way of thinking that scaling means data may be within the range of 0 to 50. Through the scalar transform, you make it 0 to 1. Because logistic regression, if you are using this to solve this problem using logistic regression, then scaling is very important. And again, you may be knowing that scaling, you have this z is equal to x minus u by lambda, where mu, this is mu is the sum of this. So if you go through this, you will see that you can have a 0 mean and 1 standard deviation. Okay, and you can actually scale. Scaling means, normally in scaling means you have a 0 mean scaling and a 1 standard deviation scaling. Okay, this is how you try to scale things. Anyway, I think this is not very important at this point. The point is here, this scikit-learn helps you to do this very automatically, very means you need not understand, means it would be good to understand these things, but even if you are not very much concentrating on the math, even the functions are very high level enough to do the job. So now once you have scaled this, you do this model training. So for you do this model training, logistic regression, which is going for you initialize with logistic regression, and you have a model fit that you have X train, Y train. X train is input feature, while Y train is the corresponding labels, and you do it for 100 iterations. Okay, so you are having a model training, and the model is logistic regression. That's why we did in the previous slide. If you go to the previous slide, you will see that logistic regression is scale sensitive. So we have already fit the data into some scaling so that now we can use the model training of logistic regression to train this system. Okay. And so then once you have this training, you have this testing. So you have this model.predict x test. So what you are getting? You are putting a x and you are getting a y. Okay. You are putting a cat picture, or you are putting a X-ray plate, and here you are getting whether it is benign. I think my spelling is wrong, but benign and cancerous. Okay. Y is giving you two labels, whether it is benign or cancerous. Okay. So once you have this model predict, but it does it on the entire test set, and then you can have things like accuracy, confusion matrix, and classification report. Okay, so it produces the reports that how good the model has functioned. So here I would like to talk a little bit about the evaluation part. Okay, so then we have understood this. There is a train. Let us just think of the basic thing. There is a train and there is a test, and in this test there is a performance. Okay, and this performance needs to be evaluated, and we have to have standard metrics which is beyond or which is independent of the model. You have to have standard metrics to do the evaluation. Okay. So I guess you have seen in the previous slide, there was the concept of confusion matrix. Okay, so what is confusion matrix? So confusion matrix is a 2 cross 2 matrix where you have 4 things: true positive, false positive, false negative, and true negative. What is false true positive? That the model has predicted benign and it is actually benign. This is the number of times, or the percentage of times, or the fraction of times the model has predicted benign while it was actually benign. So say the product has predicted benign 7 times. Out of this 7 times, 6 times it was actually benign. Okay, so then model accuracy becomes 6/7. Model accuracy, a true positive becomes 6/7. Okay, and what is false negative? The predicted benign, the model has predicted benign while it is actually malignant. Okay. Next thing is false positive. The model has predicted malignant while it is actually benign. And true negative, the model has predicted malignant and it is actually malignant. So we are seeing it from the perspective of benign. That's what is good. If we would have seen it from the perspective of malignant, this curve would have just swapped. Okay. So used in cancer diagnosis, and this can be used in spam filtering, fraud detection, etc. So this is a confusion matrix which gives you true positive, false negative, and true negative. Now what you can do with this confusion matrix is interesting. So you can have accuracy. So what is accuracy? Overall correct prediction out of samples. Okay. So when are you predicting correctly? Think you are predicting correctly when you are answering, when you are telling benign and it is benign, and when you are telling cancer, it is cancer. So what are those two? One is true positive, another is true negative by total. So overall correct precision out of all samples. When to use? Best for balanced data set where class sizes are roughly same. Okay. Now what is precision? Of all positive predictions, how many were actually correct? Okay. So what is happening? See, this is TP. So of all positive predictions, how many were actually correct? Fine. So what is happening here? That you have, again I am telling, that you have predicted benign, actual benign. Okay, you have predicted benign, actual benign, and you get 6/7. Now, just think of situation. Just think of situation where in general, when we are doing this test, out of 100, out of 100, maybe 2 are actually cancerous. Out of 100 cases, 2 are actually cancerous. Then if we just see predicted benign, okay, if we see just predicted benign by actual benign, and say 98 are predicted and 2 are cancerous. Okay, now if this 98 becomes 99, okay, you have 99 predicted benign. Okay, out of 98, 99 predicted benign. Then what is the precision? Precision is 98/99. Okay, which is also very good. The prediction is 98/99, which is very good. But if we had it opposite, what would have happened? In 2 out of 1 cases, you will miss having cancer predicted. Okay, then if this was written in the opposite way, where it was predicted cancer and actual cancer, then the precision would become half, which is very low. The precision will become half if it is very low. So what learning do we have from here? That when we are doing this, we must consider this place for cases where there may be two cases, but when we draw the confusion matrix, normally we will put cases here, prediction of cases which is in smaller numbers. So we will not do this, but we will essentially have predicted cancer and actual cancer. Okay. So what we have drawn here is not good for precision. Okay. This is good for accuracy if the number of benign cases and number of non-benign cases are roughly similar. So let me go back once and see of all prediction how many are actually correct. Use only false alarms are costly. For example, spam detection, fraud detection. So that is what used when it's costly, that you have two cancers out of which you are forgetting and you are not able to detect one cancer. Okay, that is very costly. That's why precision is used there. Okay, recall is again true positive by true positive plus false negative. Okay, so let me just, so true positive, again let me just go to this once more. So you have true positive by true positive plus false negative. This is what is recall. If you see this, true positive by false negative. So this is what is this? This is that you have predicted. So you have actually, so just let me think this through. What is false? What is false negative? What is false negative? Think this through, that you have, so there are two things which is happening in recall. I will give you an example. I think that would make you very easy things. So this is about search. So you have a search. Okay. So you are searching for, say, treatment. Searching for treatment of cancer. Okay. You are searching for treatment of cancer, and it gives you 1, 2, 3 results. It gives you 3 results. Okay. This is good, maybe 3 good results, but in the internet there may be 10 results of search. Okay. In internet there may be 10 results of search. So recall is 3 by 10. And in typical this type of search, you will try to increase the recall because you want to know all sorts of search results. Okay. Whereas if you take a case of, say, if you take a case of if you take a case of, say, citation for transformer model. You are searching for citation for transformer model, and it gives 1, 2, 3 results. It gives 1, 2, 3 results. You are happy if all this 1, 2, 3 results, if it is all 1, 2, 3 results, the model has not hallucinated. In all this 1, 2, 3 results, the model has not hallucinated, but the model has given correct results. Even 1 is good because then that is high precision. Okay. And then in many cases, you may want both precision and recall together, and you have the F1 score. Okay. In many cases, you may have the precision and recall together, and you may have the F1 score. Okay. So this is about evaluation. So this evaluation will come back again and again, and I will talk even more while I go forward. So just let us think this through once, that accuracy is overall correct prediction best for balanced data set, that if you are predicting and you are getting correct, then it is correct. If class 1 and class 2, both classes you are predicting and you are getting it correct, is fine. What is recall? Recall is of all the elements present in that class, how many elements have you been able to predict correctly? What is precision? Whatever you have predicted, how many of them are correct? Okay, we have these things together, and F1 score is a harmonic mean of precision and recall. So I hope this is fine. So we are done with supervised training. Let us go to the unsupervised part. Okay. So what is happening in unsupervised part? In unsupervised learning, we know that there was a picture of cat, again my bad picture of cat. Okay. And there was a cat written. So the label was there. But here you don't have any label. So what do we want to do? We want to discover hidden structures. So we want to discover hidden structures. If we see that all the features of some objects are similar, we cluster them. So this is what is happening. You cluster, group similar items. So similar item is a overloaded statement. How can items be similar? Through their features, perhaps. Okay. And there can be a lot of features. Say if you think two humans, they have a lot of features. Okay. And when you think of similarity between two humans, you may not consider all those features. You may want to concentrate on some reasonable amount of features. Okay, like maybe nose, eyes, ears, something like reasonable amount of features. So that's why, in order to consider any sort of algorithm, dimensionality reduction is also very important. It becomes important that when there is a lot of features, some features are very important, other features are not so important. So we have an entire set of algorithms which look into this dimensionality reduction. Okay, and this is done through PCA. And there are various sorts of works like anomaly detection, association rule, who is associated with what. And you have very important things like recommender system, spam filtering. So all Nigerian mails get clustered together and they are curved as spams. Okay. So just to give you a bit of idea, even we, many times human behavior also have this unsupervised learning inside it, distributed unsupervised learning in it. Suppose your class is ready for a group photograph and take positions in order of height. You do not possess any prior knowledge of the heights of your classmate, but slowly you begin to adjust. You try to get in a position according to the height, you figure it out without being told as where to stand. So this is humans are continuously doing this unsupervised learning and getting clusters, and we see clusters building up. Okay, so you cannot many times name why you have become friend of somebody. Okay, because there are some features which are hidden somewhere which you have figured out and even cannot explicitly tell, but you have done that clustering. And this is again used in various aspects, like this unsupervised learning, that cluster of detective novels. So those who bought this also bought this. I think Amazon, all of you see this recommender system, which is a typical example of unsupervised learning. So I have again told that unsupervised learning, the success of unsupervised learning also depend on compressing high dimensional data. Okay, what is the problem? So real data lives in very high dimensions. Okay. So images are very high dimension. Text, if we consider text, they are every vocab if is one dimension, that is a huge dimension. In genomics, there are a lot of data. So the insight is data has structure, not all directions matters equally. Like I am telling, when I am considering whether two humans are similar or not, there are many directions. We never consider all directions. We never go and see that whether everywhere somebody has their toes are big or their toes are small. Means in most, if you are not talking about running, most of the time you are not seeing that. Okay. So most variation lives in low dimensional subspace. So they are actually, if mathematically, I think that they are not very important. So we want to find out access of max variance as dimensions which really matter. And what PCA does, it finds a basis where that maximizes variance and keep top k components. Okay. So it finds out a, so just to give you an idea without going into the mathematical part, it gives you a basis where the maximum top k components can the impact or best describe the the object. The top k component can best describe the object. This is how you get it, and you get the PCA. So there are 100 dimensions, but PCA brings into 2 dimensions. That means the humans have various things, but just that humans can speak and humans can use their hand in a different way. These two perhaps would make it human. Just 2 dimensions. This is what PCA brings in. Okay. So now going to the training flow. We have the raw data. Similarly, if you remember in supervised, we have the raw data. We have the feature extractor. So we are trying to cluster murder mysteries and comedy centrals. Okay. So we have the features, we have the text. Okay. And then we have the dimensionality reduction. And from the dimensionality reduction, we get, before dimensionality reduction, it is all over the places, because some words of murder mystery are also there in some words of comedy central. So this is all over the place. Once we have this dimensional reduction, then we have clear demarcation between detective genre and crime mystery. Okay, so this is about supervised and unsupervised training. I hope I have been able to give you a bit of idea, and we will come. So we are now setting the platform to see that what are the pain points of this supervised and unsupervised training, and how deep learning can help, and which we will cover in the after a small break. Yeah, we can also take some questions. So questions are coming? Huh? Yes. Right. So again, let me tell you this thing very carefully. Okay. So let me tell you this thing very carefully that uh, see, supervised learning is about you have labels and you learn the labels. So what is happening? In short, you have dog, you have a picture of dog and the label dog given. You have a picture of cat and the label cat given. Now, this type of 1,000 pictures you may be given, and at the end, what you have to do, you have to basically, you have to basically when a new picture comes, like a child, when a new picture comes, the child begins to tell, oh, this is a dog, this is a cat. This is about unsupervised training. So, this is about supervised learning. Supervised learning has a label. So, you have to give a label. What is unsupervised learning? Unsupervised learning is there is no labels, there is clustering. So you have clustered these things together. So these things look similar. Okay. All bottles look similar. Okay. They are similar objects. Okay. Or you can say that these are similar type of people. Okay. These are similar type of people. You cannot really say what type of people, but these are similar type of people who perhaps uh, uh, would work if who are perhaps who doesn't want to do class on Saturday morning. Okay, these are similar type of people who doesn't want to do class on Saturday morning. So we don't have a label of these people, but we can tell some feature of these people. These are people who are not interested in doing class on Saturday, or these are people who are continuously taking notes. Okay, or these are books which are likely to be murder mystery. Okay, so there is a murder mystery book, and there are other books which are also similar to that murder mystery book. So you tell these books are similar to this murder mystery book. So what is happening? You cannot exactly tell what this object is. You cannot tell that what this object is, a cat or a dog. Think of a new animal, okay, whose names you don't know. So you begin to see all this sort of animals. So you can say, these are all sorts of animals which look similar. So they can be clustered, and that is what is unsupervised learning. And we do this unsupervised learning continuously in ourselves. Okay. So this is what is supervised learning and unsupervised learning. So define the rewards and penalties for an agent. Now, this is very good. So see, again, think over. So the best thing about machine learning, deep learning, it is very human in one way. Okay. So if you are giving a child, that if somebody if somebody does uh, hmm, does a math correctly, you give him a chocolate. And if a person doesn't do the math correctly, you take away the chocolate. So the person begins to understand, even if he doesn't know how to do math, the person would begin to understand, if I can do it that way, and if I can discover that way doing, then I will get more and more chocolates. So this is what rewards and penalties are, that you train the machine. So it's not only about experience, it is about feedback. This is about feedback. So I think Michel is not talking about one more thing, that more experience gives more performance. Why more experience gives more performance? Because you get more feedback, and we get more feedback through rewards and penalties. So what's feature extractor? Something which is to distinguish between memorization and generalization. Again, this is very interesting. See, think of the statement I gave, example I gave, that we have to have, we write a essay. So one thing is my hero. If I just memorize this essay and go, then I will not be able to write another essay which is like a day in the bazaar. But if I write this essay myself, my hero, and understand that there should be a introduction, there should be a main content, and there should be a conclusion, there should be tense correctly done, the words, the sentences should be short. So if you can have those feature extracted, then you escape from memorization and go towards generalization. Okay. So my question is to explain malignant and benign examples will realize. Can you please ask profession? I didn't understand, but if you are asking, yeah, this is important that when we are creating the ground truth, we have to ask professionals. So professionals first gives us the ground truth. A professional sees that, oh, this extrapolate is benign. This extrapolate is mm, is cancerous. So a professional actually gives you the ground truth. So that way, again, connect it with the supervised learning problem. That supervised learning is costly because ultimately a cancer specialist has to tell, oh, this is benign and this is cancer, this is cancerous. So his or her time is there. Somebody has to pay for that time. That way, any sorts of supervised training needs labeling, and that labeling has to be done by professional, and that is costly. Yeah, so these are very, very interesting questions. That so scalar transformation may reduce means it can reduce qualities in some cases. So again, this is a very important philosophical point. There is a mathematical point, but I will just tell you about philosophical point, that if we reduce the data, if you reduce the data, uh, the quality of the data. The quality of the data means that the various nuances that data has, does it lead to reduction in quality or reduction in its power, or it enhances the power? Let us again think back and think about PCA. What is PCA doing? PCA is actually taking a data which has a lot of features, and it is now clubbing it. No, we don't need so many features. You can work with 3, 4, 5 features, and that would be better for any task. That way, when we are doing any sort of transformation, any type of transformation may lead in loss of data information, but that may not lead in loss of data quality. Okay. And what you are telling, if not normally distributed, yeah, there are a lot of things that if not normally distributed, why do we try to make it normally distributed? I have a short answer, that because we don't miss, this is the best distribution where we can actually work well, and normal distribution makes things smoother. And if you have to work on any sorts of machine learning algorithms, smoothness is something which helps. Okay. So that how we are actually trying to make normally distributed. Okay. But this is a very good question, and I think we'll talk about this as we go forward, and we talk about this in details during our entire uh, 9 months journey. Very good. Thank you for this very nice question. Okay, so can we stop now and have a 5 minutes break? Yeah. Welcome back. Um, one is I have answered some of the questions. Other questions I will try to answer after this session. Okay. And also I will do it in this way that if there are some questions which requires a little bit of detailing, I will take it up in the next class. Next class first, I will choose some of the representative questions and also discuss it in the next class first, maybe 15 minutes, half an hour. So that we need not run fast, we need to understand things well. Okay. So let us please go on asking questions, simple questions you may think is too simple. Even then, go on asking questions. We'll patiently answer them and answer them even after the session is gone. And some of the questions, some of the interesting things, like somebody was telling, please explain PC a little more detail. We can take it up in the next class in a detailed matter. Okay. So now let us come back. So now that we have done this supervised and unsupervised model, again, let us look back and think about raw data. So this is the pipeline. There is a raw data, then there is a feature extractor. Okay, and you have supervised, unsupervised model, and you have some sort of algorithms, prediction clusters, etc. Okay. So what is the problem? The problem is handcrafted features. Means you are trying to get this nose of cats and dogs, etc. These are handcrafted features, and somebody was telling that about this. Domain experts manually define features. For example, facial landmarks, TF-IDF weights, etc. So these are domain experts would actually manually define features. Okay. Requires label data and expert feature design. Label data is by itself a pain, but expert feature design and for every new uh, new class. I think that is not, that has got just a bit stuck. But so what is happening? See, again, take this cancer example. So cancer example, you still have to have a, from the plate, you have to have a expert who will say that this is cancerous and this is benign. Okay, this is we have understood. But even beyond that, the expert has to say, see, this, follow this. So this is, if this is the X-ray plate, I'm just writing X-ray plate. Okay. Even more, the expert has to tell, oh, this part, because this part is more white, or this part is more white, that's why you are thinking this is cancer. Okay. So then this domain expert also handcrafted features. He or she doesn't see the entire picture, but he or she actually handcraft features from this X-ray plate and give it to you. So there are two types of things which domain expert does. One is giving the label. Okay, that cancer, non-cancerous. Okay. Another is also telling you the exact features and how to extract those features, exactly where to look. Okay. So this feature extraction is also a very difficult task and it requires domain expertise. And so it will not scale. Okay. In case of unsupervised learning also, so you have to have handcrafted features like what counts, even if you are doing PCA, the PCA access. So this has to be chosen maybe with some heuristics but it has to be chosen by experts. So this does not generalize across domain with manual redesign. So the point is simple, that so the entire pipeline is dependent upon a good feature extractor. So we are again and again telling, so if we take the cat and dog example, and if we extract the tail for both dog and cat, it may be much more difficult to identify from the tail whether it is a cat or dog than from the face. Okay. So feature extraction is actually the key of many algorithms. This is the basis of algorithm. If we cannot give good features, the algorithm cannot understand. And to understand these good features, we are primarily depending on experts, which doesn't scale. That's why I have written costly, slow, and brittle. A new domain needs a new expert. So this is where machine learning becomes problematic, or it cannot scale. Okay. And this is where the embedding comes, the learned embedding comes. Okay. The solution, learned embedding. It is automatic. The model learns which features matters directly from raw data. No human labeling of features required. So the model will learn which features matter directly from raw data. So this is transferable. One embedding model generalizes across tasks, classification, clustering, search without redesign. So it is the same embedding model. If we are doing this feature extraction, this same embedding model would then it can actually feed to any supervised, unsupervised, or search algorithm, etc. So, and what it happens, it is dense and scalable. It compacts low dimensional vector, capture rich semantics. So I will deconstruct this low dimensional vector captures rich semantics. Okay. Geometry encodes meaning. I will actually reconstruct this. But just to understand one thing, that what we are trying to do, we are trying to automate this feature extraction. This is what the first step is needed for scaling machine learning. You have to automate the feature extractor. Okay. And now when we are automating, we are actually learning a representation. Okay. And if you remember, if you know, the top conference in machine learning is called ICLR. Okay. And what is this? International Conference for Learning Representations. Okay. So it is learning representation, which is the holy grail of machine learning, that you have to learn good representation of raw data. And representation means what? Vector. First, let us just think of vector. Okay. Representation means vector. So why vector? What is the importance of vector? See, the point is, when there is something like a cat and a dog, just let me write here. So think this carefully. Okay. When there is a cat and a dog, cat and dog. So if I want to understand distance between cat and dog, if I want to say the distance between cat and dog, can you tell? It's very difficult. What is the distance between? When you are asking a stupid question, you may tell me, why are you asking such a irrelevant, stupid question? What is the distance between cat and dog? But when cat is converted to a vector and dog is I'm telling cat's representation is converted to a vector and dog's representation is converted to a vector, then you can calculate the distance between two vectors. So suddenly you see the power which is coming. Suddenly, when two objects which we could not calculate the similarity or distance, although we have some idea that cat is closer to dog than mountain. We can always think that cat is closer to dog than mountain. We had an idea, but essentially quantizing that was difficult. But as soon as we can convert to a vector, then we can use all sorts of rich mathematics of vector to calculate the similarity and difference between cat and dog. Okay, this is first thing. The next thing is low dimension. So now you can think of a trivial thing that all the elements in the world is each are one vector. All the elements of the world is an axis. Okay. If we have three elements in the world, then there are three axes x, y, z, and element 1 is 1, 0, 0, element 2 is 0, 1, 0, and element 3 is 0, 0, 1. Okay. So then this would be a huge high dimensional vector. Okay. A trivial representation. But that may not be so useful even if you can do some calculations. That calculation in a very high dimensional space may not be very important. So not only vector, we have to put it in a low dimensional vector. Okay. Which will then capture rich semantics. Okay. So I will come to this. Okay, I will come to this. So essentially, if you think of this low dimension of vector, then say dining and restaurant. Okay. These two, I don't know whether my spelling is wrong, right or wrong, but dining and restaurant, these two vectors would come very close to each other. Okay. So this is actually what is very important. Fine. So what we are telling, essentially we have to do this feature learning through embedding. Okay. So there are object 1, object 2, object 3, and there is an embedding model which would put it into a vector. So embeddings are powerful tools for representing complex data in compact form while preserving semantic meanings. Just note this, while preserving semantic meanings. Okay. So what is semantic meaning? Semantic meaning means I have told that the vector of dining and restaurant, or dining and say dinner, or dining and lunch, or dinner and lunch, this should come close to each other. That means it is somehow preserving a semantic meaning. So let us see this. How do we feature learn? Through embeddings. So say this, we have this raw text, the cat sat on the mat, and we have to have some representation and have to have some classification. Okay, have to have some classification of this cat sat on the mat, and we have to have some classification whether this is a positive sentence, negative sentence. It has many sorts of classification algorithms which we can do. Okay, or generation, what would be the next sentence? So there can be many sorts of things which you can have. So the first way, so since we have told that we have to have a representation, the first way is to have a one hot representation. Okay, so cat, dog, king, queen, apple, runs, everything is one space or one space. Each word is a point in a high dimensional space. The one is at index at I, everything else is 0. So this is a high dimensional space. Here you have 1, 2, 3, 4, 5, 6, 7. So 7 dimensional space. Cat has a 1 in the first dimension. King has a 2, 1 in the as a 0th dimension. At second dimension, king, queen has a 3 dimension. So this is how we represent, and we call this a one hot vector representation. So assign every word a unique index in a fixed vocabulary. Okay. So then we have a simple thing that we say that there are sentences, the cat is happy, and you have a vector which is maybe the sum of all the vectors of the cat is and happy, and you have the dog ran away, which is sum of all the vectors of the dog happy, and then you have a linear classifier and you begin to say which is a negative sentence and which is a positive sentence. Okay, the cat is happy is a positive sentence, while dog runs away maybe not so positive, it's a negative sentence. Okay, so what works? This is a simple, fast, interpretable weights. Works for what frequency signals also means maybe cat, maybe if it's cat is happy, cat is there, say, then this may become two, something like that. Okay. So this is something which is happening, but what struggles? If we have this sort of things, happy and joyful are treated as unrelated. And this is a sparse vector. Okay, and it will increase as the number of words increases, the vocabulary size increases. Huge, mostly zero input. So sparse vector multiplication, etc., they are theoretically possible, but even then they are not so easily manageable. Okay, and unnecessarily that creates burden. Okay. So, what I want to say, there is obviously one issue with the basic concept because these two are not coming together, but there is also a issue with implementation. Okay, because you have to implement such a huge factor, which is not a feasible thing. So, just to tell you again that no semantic meanings, these vectors don't have any semantic meaning. See, if I think this king and queen, if I think this king and queen, what is their similarity score? Similarity score is zero, because they are not overlapping in any places. Okay, but this should not be. Okay, two unrelated dimensions. So, and cards of dimensionality. So that's what we are saying again and again. The 99% of the entry are zero, which makes it a 100K D-inverse network. And if you have to learn something at very, very high dimension, that means you also have to have a lot of data to learn that. So this is again the dimensionality put a cards on you to learn. Okay. Then no word order. So simply dog eats man and man bites dog. Okay. Hopefully that never happens are same. Okay. So these two become same. So we are having a bag of word assumption. Basically, we are having a bag of word assumption because again, if you go back and think, every place is one. Dog is in the first place, king is in the second place, queen is in the third place, apple is in the fourth place. So every place represents one element or one word, and it doesn't matter whether that word was at the beginning, at the end, in the middle. It doesn't really matter. Okay. And then there are out of vocabulary. So new word coming now, of you have trained it on dog, cat, etc. And suddenly kangaroo comes. Okay. Then what will you do? So out of vocabulary words have no info and it really cannot work. So these are fundamental flaws. So we need smarter representation. I hope I have been able to impress upon you that why we need smarter representation. So why sparsity breaks similarity? Again, I think I have told it, but again, let me just tell that cat and dog, kitten is as closer to happy and dog because all are zero. So one-hot vectors are orthogonal by construction. The model can never discover that the cat and kitten are related. We need a representations where similar words are also geometrically close. We need a representation where similar words are also geometrically close. Okay? So, what is the big idea? Now, distributional semantics, I'm telling it from distributional semantics, but this is what you will know from other things, words by context. So you shall know a word by a company it keeps. Like you will know a person by the company it keeps. So J.R. Frith uses that in his own way and says that you shall know a word by a company it keeps. Okay. So the big idea is the word's meaning is defined by the words that frequently appear around it. So there may be a context window plus minus k words on either side of the target words. And you build a vector from the distribution of the context words across a large corpus. Similar context, similar meaning, similar vector. So think now, if you think of these two terms, boy and girl, okay, and think about two words, just two words which will come before boy and two words which will come after boy. They will be very similar, means many of them will be repeated again and again. So what happens? Similar context means there are similar meanings and they will have similar vectors. Okay. So now see this context window of banking. So banking is government debt problems turning into banking crisis as happens. Okay, turning into crisis as happened. And then saying Europe needs unified regulation to replace, given its system a shot. Okay. So these context windows will represent banking. Okay. So you see the interesting word is coming like regulation, okay, crisis, okay. So which may not come with normal banks and banking, okay, which may not come with river bank. This context will not come with river bank. So this banking representation will be a contextual representation and river bank will have a different representation, okay. So and it will be based upon the context. So instead of a word position in a fixed vocabulary, we encode what words it co-occur with. Count of co-occurrence, compress, and then you get a tense vector. This is the road to word embedding. So I will not talk about how we do the embedding here, but what is happening, count of co-occurrence that you compress in some way and you get a dense vector. Okay, you get a dense vector and this is the road to word embedding. So see this. So you have something like replace a one source one vector. So you have 0 0 0 1 0. It is a very high, maybe 500 dimension, 50,000 dimension. That becomes a dense vector in 300 dimensions. Maybe every values carry some meaning. This is 0.32 minus 0.7, 1.5, etc., etc. Every values carries some meaning. So here, what was it? 99% similar zeros. No two were similar, so not similar, and it required a huge memory. But now when we are learning these weights, I'm not talking about how we learn these weights, we'll talk about it later, but just think that there is a machine which learned these weights, then all values become active and there will be geometry. I'll just show you the geometry which is meaning, and you have compact and fast. So see, there is geometry, there will be similarity. Obviously, we are talking here, I'm talking this again and again that now the embedding of kitten and embedding of cat would have, maybe if I write similarity, embedding of kitten, comma, embedding of heart, that will be very high. Okay. That part is important, is understood, and this is what is written here. You see the cosine similarity of vector of cat and vector of kitten is around 0.92, which is very high. Okay, but also there can be geometry, like you see vector of king minus vector of man and plus vector of woman gives you vector of queen. This is very, very interesting. See, you have king, then you have man, and then you have woman. So you add these two vectors and subtract, no, sorry, you add these two vectors and subtract the man vector, then you will get the queen vector. So you have queen, man, and woman. So you add woman and king and subtract man, that will give you queen. This is actually even stronger than the cosine similarity. Or you can have vector of Paris minus vector of France plus vector of Germany. You will get vector of Berlin. Okay, why? Because somehow vector of Paris has that generalization of capital. Okay, vector of Paris is not just vector of Paris, but it has that generalization of capital embedded in it. So as soon as you are subtracting Paris, then only capital stays. Only the concept of capital. It is somehow capital of France. So as soon as you are subtracting France, then France goes, only capital stays. Now you add Germany. So this may look like a little bit of black magic, but this is what happens, that then you have Germany, capital of Germany, and you get Berlin. So this is how representation, and now it goes even beyond what experts could have done. So you are taking one step backwards, but this has surged you 2 steps forward. Fine. So to again get it clarified and get it in a compact way, that the embedding model learns dense vectors from raw data. No handcrafting is required. So what are embeddings? These are dense numerical vectors representing objects in a high dimensional space where similar items clustered together. Okay, in a high dimension space where high dimension means not very high dimensions, but maybe high dimension is 30 high dimension or 600 dimensions, okay, which is high dimension space, not like million dimension, okay, where similar items clustered together. How the model learns? Objects fit into the embedding model, which captures a fixed length dense vector capturing each object's semantic relation. So you have the objects, you have the embedding model, and that gives you dense vector, and these say something like this are dense vectors which have similar semantic. Okay, so why embedding means, again I have told you, but let me tell it again, no manual engineering needed, captures latent structures, enables similarity search, clustering, and transfer learning. And this could not be done through expert-driven feature engineering. Okay. So input any raw object, model neural network trained to end on a task, dense fixed length vector for every object. Similar object sits nearby in the vector space. Okay, I hope this is very clear about feature learning through embedding. So this brings up the basic thing which we will talk about in the next many months. We are together for many months about deep learning. Okay, so deep learning is about feature learning. Neural networks learn complex features from simple one through multiple layers. It learns those features, learns those latent. Okay, and there is no manual feature selection needed. Just you give a picture, the learning will happen. Models automatically identifies the most relevant features from raw data. So this is a part of learning. See, in original machine learning, I will just go back again once more. Maybe many of you understood, but I'll just see that these two are separate models. Think of this carefully. These two are separate models. The feature extractor is a separate model, and the supervised unsupervised model is a separate model. But here, many of you may have heard deep learning is end-to-end. What is end-to-end? Why do we call it end-to-end? Because these two models actually merge. that you do the feature selection or feature extraction along with learning. So the two things goes together. Okay. Fine. So I guess we know that this has a practical application. I don't know why I have even written that. Effective in areas such as computer vision, natural language processing, and many, many fields. Let me just write and many, many fields. So a little bit of background, but not so much is important. That how did initially, I'm telling it like again, because of my age, I can tell many things that when this were people were working on it in even early 90s, and there was actually thought to be that this is thought to have some biological inspiration because we had these biological neurons and there are dendrites which receive signals from other neurons and there are cell body integrates incoming signals. Okay, they integrate in incoming signals and axons are transmits output signal to the next neuron. So there is some place where through signal comes, some place where you have the signal been assimilated, and there is some place where the signal is transferred. So what happens is basically in humans it is thought that it is thought that this memory or this knowledge is distributed across this area. Okay. And here it essentially happens that there is some input x1, x2, something like that, which is like dendrite, and then there is some weights, okay, which is like the connection points, the synapse strength. Okay. So you have x1, x2, x3, xn, which are like dendrites. You have the weights which are the synapse strength. Then you have a weighted sum which is actually accumulating this weight and putting it into a z, and this z is passed through a activation function fz. This is passed through a activation function fz and it outputs pass to the next layer and it produces the output. And what is learning? Like here, learning is adjusting the weights like synapse strength. You adjust the weights. So initially you may have very random weights in your brain, but as you gain experience, etc., the weights in your brain begin to adjust. Okay. And we know that old people cannot learn much. Okay. Old people like me become slowly less learnable. Okay. Why? Because these weights becomes more and more plastic and you cannot change the weights. Bodily, biologically, your weights don't begin to change. So weights are the secret sauce of learning. How you adjust your weights, based upon that your learning goes. Okay. So now to tell this, I hope the very basic idea is clear to you. Okay. Very basic idea is clear to you. I will tell you in one words. It is about feedback and adjusting weights. So it is about feedbacks and adjusting weights. Okay. So then there is one thing, it is about representing. So when you adjust weight, there are two things which happen. It is about representing an object and it is about task, about classifying. Task may be classification. Okay. So I will pause 1 minute and think about this. Let you think about this. So it is about feedback and then adjusting weights. And what are you learning when you have these weights? You are learning representation, how to best represent raw data, and also you are learning a task. So when you are learning a task or task optimization or task, you are learning to execute a task, a classification task, you are also learning representation. So this is very interesting. Again, it may look very simple from apparently, but think if it's of humans, you have a task. You have a task of passing an exam. Say you have a task of passing joint entrance exam. Okay. So that task you do the optimization. But in process, you also learn a much better representation of say mathematical constructs. So that mathematical constructs learning, that representation actually is task independent. You would have learned it, you would have learned it anyway, even if you have not got good score in JEE or bad score in JEE. Okay. So there are two things which you are learning. One is you are learning to optimize that task. You are learning to optimize how to get good score in joint entrance exam. But also you are learning how to do good math, and which may not have anything to do with joint entrance exam. Okay. So there is two learning. Again and again I am telling, there is a explicit learning, the task-based learning, but also deep learning is bringing you a very, very important thing. There is a implicit learning, learning representations. Okay. So this is something which we many times don't really get it, that we are not only doing the task, but in the process of doing the task, we are also getting something inherent. We are getting something inherent knowledge, which may be useful for any other task. And this is very human. If you think, this is extremely human, how humans behave, how humans learn. Okay. So then we have, that's why it can do so difficult things like document summarization, caption generation, etc., etc. Okay. So the first, we'll talk about the first uh, perceptron, uh, the first neural network, which is the perceptron. We will talk about the first neural network, which is the perceptron. So what is perceptron doing? So there are inputs x1, x2 up till xn. Okay. There are inputs which are x to xn. And this z is summarizing, is summing up. Okay. It's summing. It's a weighted sum. W1, x1, W2, x2, W3, x3 plus B. B is a bias. Okay. So this is a summation of W1, xy, Wi, xi plus B. Okay. So you have a summing up of all these weights, all these inputs. Next is that you have an activation function. So what is an activation function? It takes in this Z, you have a Z, you have an activation function fz, and it produces y hat. Okay. So activation function is typically a nonlinear function. So see, this is very linear. Huh? There is just a addition, summation. Okay, this is a linear function. Now, whatever is the output, you pass it through a nonlinear function and get the output. So learning adjust W and B to minimize prediction error. So you have to have some sort of adjustment of W and B to minimize prediction error. Perceptron can only learn linearly separable. So I can go to that we may ignore that for the time. But I guess you are understanding that x1, x2, xn, you have a z, and you have a z, and from this z, you have a activation function, which again converts this z, which is a linear sum, to a nonlinear function or a nonlinear transformation. So this nonlinear transformation can be many things, like we have a sigmoid thing. Okay, sigmoid is 1 plus e to the power minus x, but importantly is nonlinear transformation breaks it into two class. Okay, it breaks it into two class, like it breaks it into a positive class and a negative class. So even if you have something like this, it will break it into two class. It is breaking it into two distinct class, which tanh also does. The ReLU is something which just have a linear translation, in the positive axis, while in the negative axis it makes it all zero. Okay, so it has a linear translation. It is still a linear function in the positive quadrant, but it makes it zero in the negative quadrant. And leaky ReLU is something like that, which makes it linear in the positive and also linear in the negative, but the gradient in the negative is much lower than the gradient in the positive. Okay, and L means max out is something that you do various sorts of sampling and take the max. Okay, you can you can and run the perceptron 5 times and get 5 z, z1, z2, say z5, and you take the maximum. You can get the maximum z5. Okay, something like that. You can do a max out sort of things. And LU is something which is linear in the positive, but it has a function which is a very slow growing function in the negative direction. So all these things is basically making your linear summation to something nonlinear. Okay, and why nonlinear is needed? Because linear captures a level of reality. Our reality around the world can be classified through nonlinear. Reality around the world can be that's fine. Can be captured around nonlinearity. Okay. So then we go from a single layer perceptron to a multi-layer perceptron. So you have the first layer, then from there whatever the y is the output, that is taken to the second layer, and then that is taken to the third layer. In this way you go through various layers of summation and activation. Okay, summation and activation. So this way you get a transformation and slowly you begin to have a very complex function. Means potentially you can have a very complex function to capture the task. Okay, to capture the task which you are given. Okay, maybe a classification task which may have a very complex, say a classification task like this. Say you have these are positives, okay, and these are negative. Okay, so you can now capture a very complex terrain like this through this sort of perceptron. Okay, so it is not just a linear thing that these are positive, these are negatives, and you have to try to build a negative. No, but you have a very complex things, and that can also be captured through this strong nonlinear functions. Okay, fine. So information flow from left to right through hidden layers. You have a feature learning to output the prediction. Now, let us just think this through once more, that you have a forward pass, input flow through network produces vector y hat. Okay. Loss function. Now we will come to this loss function. I think we had this reward and punishment, this concept somebody asked in the first session. So this entire reward and punishment paradigm is denoted as loss function. Okay, here we denote as loss function, and loss functions are various things. Like in regression there can be MSE. Okay, um, and in normal classification there can be cross entropy loss. Okay, there is a cross entropy loss. I can talk about it in more details, but there is a cross entropy loss where we are seeing the cross entropy between the ground truth prediction, ground truth data, and the predicted result. Okay, so you have a cross entropy loss. Okay, so you get some loss L. What will you do with this L? That is the question you may want to ask. So this L, so you compute the gradient of loss with respect to each weight using chain rule. So if you want to calculate the weight with respect to dWdl, then you have the loss with respect to the output. Okay, with respect to this output, you have the loss with respect to this output that you know. Then with this output, you perhaps know the loss with respect to Z. What is Z? Z is the, so let me just go back. So go back to this picture to tell you this thing. See, you have Z. Just remember this. You have Z, you have Y hat, and you have X. Okay, just remember this. So you have the weight. So this is dl, dw, dy hat, and dy hat, dz, and dz, dw. Okay, and you have this chain rule at every layer. Sorry. So once more, you have dl, dw, and how does it come? dl, dy hat, y hat is the output. dw, dz, dz is the output of the summation. And what is w? W was the weight by which the summation was done. Okay. And in this way, you can understand how much the weight loss has become, because loss has come because of the weight. Okay. If it is very high, that means if you change the weight, then the loss would go minimize. That's why you have a gradient descent update. W is equal to W minus N. N is a learning rate. I will coming to this dl dw. Okay. So what is learning rate? Okay. So learning rate is nothing that, again, all these things, if you can think this is something like this. You are actually climbing some sort of hill climbing or valley climbing, whatever you tell. You are coming down slowly, and you want to reach the meaning. This is what you are doing essentially. And what does learning rate do? That you can hop like that. It stops that, says no, slowly, go slowly, so that you don't miss the minima and you come to the right point. And that is what is called learning rate. And but it should not be again too small. If it is too small, then what happens? You may take infinite amount of time to come to the minimum, which you don't want. Okay, so this is learning. So all these things are small nuances, but I'm just telling you again and again, so that this would be needed for your entire 96 hours, and you should have this thing, basics very clear. Okay, and you can have various sorts of variants like SGD, mini batch, Adam. Okay, all modern optimization. And various challenges like vanishing gradient, overfitting, local minima. We'll talk about this in small details as we progress. So I want you to understand the backpropagation very clearly, so that this doesn't have any problem with you in the future. So I'm taking a very simple example, and these slides are taken from the Stanford thing. I think this is very good. I guess Andrew Ng teaches this course. You can go and see these slides also. So what happens? you have a simple back propagation. Say you have a function x, y, z. So x, y, g. So g is perhaps the weight. I'll think z as the weight is equal to x plus y, z. Okay, x plus y, z. Now, for example, now let us think initially x is -2, y is 5, and z is -4. Okay. So what happens? Q is x plus y. Then dq dx is 1 and dq dy is 1. You can understand dq dy is 1. Now, what is f? F is qz. Q and z. F is qz. So then df dq is equal to z, while df dz is equal to q, because you are doing partial differentiation. Okay. When you are doing the q, z becomes constant. When you are doing z, q become constant. Okay. So now you want df dx, df dy, df dz. Okay. You want this. I hope this is clear to everybody. Okay, so now f is -12. So df is 1, obviously. df is 1. Clear? Okay. Then df dz. df dz is how much? What was df dz? df dz was q, and q is 3. So df dz is 3. Fine. df dq is z. So df dq is -4. And from the chain rule df dy, what is df dy? Is df dq and dq dy. So df dy and df dq is how much? This is -4, and dq dy is 1. So this will be -4. Similarly, you can have df dx. This is df dq, df dq. What is df dq? This is again -4, and dq dx is 1. So this will be -4. So you have 3 -4 -4, 4 -4. Okay, clear? And let us think just for sake, if we consider the weight z, z is somehow a weight and learning rate is say 0.1. Then the update value of z would be z is equal to z minus the learning rate into df dz. And this become -4 minus 0.1 into 3, and this becomes 4.3. So weight z is not slightly opposite to the gradient, reducing the loss with each step. So if you are nudging a little bit opposite to the gradient, that means this will reduce the loss in each step. Okay. So you are actually trying to do loss minimization, and you are telling that if you propagate this loss in this way, you are doing a bit of loss minimization. And this would happen again and again and with a lot of data, and ultimately all this will begin to stabilize and the weights would begin to stabilize. And what will happen? More data if you give, the weights will not change a bit. That means the system is well trained. Okay. So this is what all about machine learning. Okay. This is all about machine learning and how machine learning behaves. Okay. I guess you are getting an idea, very good idea. So again, let me just tell you what is happening. There is a system, and this system has a linear part and a non-linear part. Think carefully. There is a system which has a linear part and a non-linear part. And this is a block, and this block is repeated again and again. Okay. That's why you are having multi-layer perceptron. Okay. And since this linear layer has some weights, okay, that weight needs to be adjusted. so that you get the best one. So you are all playing on that weights. And how are you playing? You are actually propagating the loss and accordingly adjusting the weights so that next time the loss becomes minimum. So it is all about weight updation and loss minimization, and that is done through gradient descent. So maybe you not later not remember exactly how it works, but think this through. Have this basic thing in your mind that it is about loss minimization and weight update through gradient descent. Okay. So this is very good, but it is not without thorns. So there are various lot of issues. Lot of issues also crop up. Okay. Like we called a bias variance trade-off. So what we say is like underfitting. So underfitting is where model is too simple, cannot capture patterns. Okay. Overfitting, model memorizes training data, fails on new data. Again, this is overfitting means again that memorization concept. Now you have marked in 5 essays completely and gone to exam. In exam, you thought one of the 5 essays will come, none has come. So this is model memorizes on training data. If one has come, you would have got 100 out of 100. Huh? Suddenly one didn't come, you are getting 20. So then this is what that model memorizes on training data, fails on new data. So you have to have some sweet spot that generalizes well to unseen data. Okay. So then what you say, okay, it may not perform very good on training data. Like again, I'm just again telling essays because something is personal, very personal to me also. That okay, you read the essay once, whatever is written in the book, my favorite hero, read it once and just reproduce it. You can tell the kid. So the kid will not write as good as the book has written, but it will generalize well. The kid has a lower training efficiency or lower training accuracy, but it will have a higher testing accuracy. Okay. So that is the sweet spot which you are actually looking. Generalizes well on harassed data. And this will be monitored via train validation. I have never talked about validation. I'm using a new term, train validation test set. And training accuracy versus validation gaps would mean a overfitting signal. I will come to validation. And then how to solve this? There are regularization techniques L2, L1, there is dropout, batch normalization, data augmentation, early stopping. So there are a lot of different techniques, and these are techniques as practitioners, all of you should know and all of you should understand and use it. Okay, I will detail them slowly now. Okay, let me detail them. So the first is underfitting. So what is underfitting? Underfitting is that the model is something like this, you are drawing something like this. So model too simple, misses patterns in training data, high bias, low variance. Okay. Degree 1 polynomial on the curve. So it's just a degree 1. Good fit. So good fit is not exactly fitting all the points. This point is not fitting, this point is not fitting, this point is not fitting, but it has a low bias and low variance. I will talk about that. The goal of every model. Okay, it shouldn't be have very, it should good fit, but overfit model too complex memorizes noise. Okay, so it has a low training data, means it is memorizing this. It would have been better if you had memorized this. Low training error, high validation error, high variance, and low bias. Okay. So this is how models are overfitting underfitting, and have a good fit. So then what is bias variance? You are having a sweet spot. You are having a sweet spot. So you have model assumption is not too rigid, increases training error. High variance means overfitting, model too sensitive to training data, validation error diverges. Okay, so you have this, you have a model complexity. Okay, the bias is this one. Okay, the bias goes down. Okay, and the variance goes up. Okay, and you are looking for something. Okay, so what are you trying to do? You are minimizing the bias and you are minimizing the variance, and and see, none are noisy data. None are means you cannot have data which has no noise. So there will be some irreducible noise always. So like you know that it is impossible to create a room where there is no noise. It is absolutely impossible to create a room with no noise. So there will be some noise. So the total noise is some bias, variance, and irreducible noise. So how do we do this? Okay, how do we do this? We do it with some regularization. So what is regularization? So regularization, okay, so I will talk about regularization, but regularization, before that, let us talk about training and validation run. So what is training set? So we have a training set, we have a test set. Okay, we also have a validation set. Okay, so the test set is out of reach. So you don't see the test set, but and you don't see the validation set while doing the test set. Okay, while doing the training, you don't see the validation set while doing the training. After you have trained, you test it on validation to understand how much generalization has happened. Okay. If it has generalized, then the validation would be very good. If it has not generalized, then the validation accuracy would not be good. Okay. So this is what validation is: a small amount of data set which is kept aside and which is used in the grand scheme of training itself. But when the basic core of training is going on, validation is not used. Once you have trained, you see how good training has happened, and use validation in the inference stage of the training, and you then decide, oh no, this is not good, this is not generalized, and you can repeat the training again. Okay, so see what happens if you go on for various epochs without regularization. What is regular? So next is, what is regularization? Regularization is something which is adding some noise to your accuracy. So suppose you have got 99 out of 100 in some exam. Okay. So now as an examiner, I say, see, you have got 99 out of 100, most probably because you have got the questions have come common, means the questions which you have prepared, those questions has come, that's why you have got 99. Okay, and you seriously don't deserve to get 99, please get 95 or 94. Okay, which you may not like it, but this is what about regularization. Regularization is telling that it is telling that whatever you have been evaluated on, that is only a partial view of your capacity. You should have some sort of regularization which says that you this is this is something which tells that, see, you have not seen some data and you don't know how will you perform on that data. on that basis, I am thinking that you may perform good, bad, etc. I am giving you average marks on that data. So I just means I can give you exact formula, but again to just understand the concept, let me just think this way so that the logic is clear. So your exam is on 80 and you have got 79. But the examiner is telling the next 20 is the unseen part. I really don't know how will you perform. So you are getting 10. Okay, which may look weird, but this is how it is because you are telling that this may be very difficult, etc. You are getting 10. So ultimately, you will get 89 out of 100. And this is something which is regularization and which actually says somebody who has got 70 out of 80 is not as bad as you think because that person is getting 80 out of 100 and you are only getting 89 out of 100, which is almost closer. So your immediate learning is not given full importance, it is given importance, but whatever you have not learned, that is taken into consideration. And that is regularization, which is put in various ways. As you go through your course, you will see regularization will be put in various ways. Okay. So then what happens? What is the impact? So if you are giving some regularization, as epochs increase, if you don't give some regularization, as epochs increase, what happens? This person who is very exam friendly, he only optimizes for that exam. Okay. And as a result, as soon as something outside that exam comes, the gap increases. Okay. So the person says, oh, anyway, I know how this exam says this is a multiple choice exam. I know how to max it, and I will do that type of question. And as soon as non-multiple choice course comes, you see that there is a lot of gap. But if you are punishing him and again reminding that person that yes, you have got good marks, but that is not enough because there is something even beyond that, and you have to learn beyond that, and you don't forget that, then you see that the validation loss and the training loss are doesn't diverge after some time. Okay, they stay together. So it is regularization is something like keeping people to the ground. Okay, some people get a lot of success and then say think that this is the only truth. But regularization says there are other truths. You have perhaps got success because you had some some things very special at that point. That doesn't mean that you fully deserve it. Means it may be that there is some chance factor also, and you should keep that in mind so that you don't get too much consumed by your success. Okay. So what is regularization? Again, now I am coming to the technical part. Okay, adds a penalty term to the loss function to discourage large weights. Okay, forces the model to stay simple and generalize better. So this is something like this. So you have a rich function. This is loss plus whatever weights are there. You are doing a lambda. Swings all weights smoothly towards 0. So what is happening? The larger the weights, the loss function becomes larger. So then what would the weights trend to do? It would trend to go towards 0. And lasso is again similar, but here there is a square, here there is a mod. Okay, and lasso has this feature, you can go and see, search it, that it drives some weights to exactly 0. Okay, so this is how it begins to happen, that in this rich functions, weights smoothens up and has a lot of various bits. While if you use lasso, you will begin to have 1 and 0. Okay, you will begin to have 1 and 0. Okay, this is how it begins, and you can also see this. I've put the scikit-learn and thing that you have a ridge and lasso, and you can have linear models, impose ridge and lasso, and you can do ridge regularization, or you can do a lasso regularization. Okay. So again, think this through carefully, that what is happening, what are you trying to regularize? That you are trying to regularize that, see, the weight should not become too high. If weights become too high, then some of the weights would have a lot of impact, and I don't want to give lot of impact. I want to keep the impact minimal, and that's why you are putting this as a regularization. So more the weights, the loss goes that way. Okay. So again, I have told you, I think I have told you that then the lasso creates parts model. Okay. It pushes weights to zero. Okay. While ridge swings weights evenly and it gives a even weight. Okay. And Miss Lasso means, again, there are other things which I don't want to bring in. The ridge has this differentiable thing, and it has some analytical close form, while this lasso is difficult to have that. That is non-differentiable. Okay. You can understand that any mod function is not a differentiable function. The next thing is dropout. So dropout is also very interesting. Okay, it randomly zeroes out neuron during training, forces network to learn redundant. So say there are neurons here. So you tell in this training these neurons will not work. In training phase 1, these neurons will not work. In training phase 2, these neurons will not work. So you are actually dropping some of the neurons and not allowing it to work. Okay. Why? This question may come out why. So it happens. See, again, I will give you a real life example. Say you have told people to do some, you may have some capstone project. So you are telling people to do some capstone project. Okay. And they form groups. And it will so happen that only a small amount of people will do the capstone project. Okay. And those groups, and they will form groups again and again because they find each of them useful. So they will form groups again and again. So what will we have? Ultimately, you will have some set of people who are good at learning, who have learned things well, and some who have not taken any burden of learning. Okay. So this is what we want to stop with this. This is a very simple thing, very real life. As teachers, we try to do. We try to say, no, this time these 5 people will work. Others have a holiday. And now you form group within these 5 people. Okay. So this is how this dropout rate works. Okay. And then we have this early stopping. So early stopping is you are monitoring validation loss and you stop training when it improves validation, when it stops improving. So you have seen this again, this thing. So you are seeing that your validation loss is slowly here, is really not coming out, but say it is slowly coming out and then begin to increase. So at this point, stop. So you have an early stopping. You may have thought that you will run the system for 50 epochs and slowly get the weights trained. But now you are thinking, no. At 30 epochs, I am seeing that the train loss and the validation loss are diverging. So anyway, I stop here. Whatever I have trained is trained. I am happy now. I am dropping here. So this is what is called early stopping. So essentially, again, let us think this through, that it is all about a lot of techniques. It is about understanding the basic underlying theory well, but then understanding various techniques which can be used to overcome the problem. So many of these problems may come when you are training. See, again, deep learning, machine learning, generative AI, these are not panacea. Huh? People have to really work hard and run the system. And it doesn't come like that, that you tell Claude to tune a system and it will tune a system. It may help you a lot, but then the intuitions, the understanding, the tools which can really execute your intuition, those are the things which you need to understand. And it is all about understanding and getting a grasp on all these sorts of techniques. Okay. So finally, I put it together, and we have a scikit-learn pipeline which we will share with you. Okay. So you import all the things, then you have the random um, data creation. Okay, then you have the feature extractions. Okay, you have the feature extractions, and then you have the training and the testing. So, and here you see the feature extraction, and you have the regularization. Okay, you have the regularization pipeline. Okay, you have the data creation pipeline, you have the package uploading pipeline, then you have the training pipeline where you have the cross validation going. Okay, so again, always hold out on test set, never tune on it. Use cross validation to get stable performance effect, and tune alpha with some grid search or validation. Alpha is the rate at which you will have the learning. You can actually do it through some algorithm like grid search, Sylvie, etc. etc. So I hope I have been able to give, this is the uh, uh, I hope I have been able to give a bit of idea about how things are. Okay. And we can again go back. Means this is very basic, I know, and many of you may be knowing it, but this is the basis things and basic intuitions which we need to understand to go forward and build up our CV, our knowledge system. Thank you. Okay, very good. So I did not understand sparse vector. Can you explain, please? Okay. So see again, can I write here? No. So no. Okay, doesn't matter. So what is sparse vector? See, sparse vector is, think about this. I have given you example. Say each word is a vector in one dimension. So say you in English language there are 1 million words. Okay, there are 1 million words, and you have a vector of size 1 million. Okay, where a one each word has a 1 and all zeros. So what you have? You have 1 million dimension. You have 1 million dimension, and you have in in this 1 million dimension, each dimension just have one vector. So that is what is sparse vector. Okay. So you have 1 million dimension and you have just one vector in each dimension, which is sparse vector. Okay. I guess this is clear. Next question. So Pran, go with us. How evaluation is evolution or evaluation? Not, huh? It was evolution, huh? Evaluation or huh? Evaluation. So yeah, I'm not so clear about the question. What exactly you are trying to ask that, and uh, but what is see there is what is embedding? Embedding is okay. The best example of embedding is a map. Think that if you think that our globe, our world is round, we cannot hear Professor Bolser. Can you hear us now? They cannot hear. Tell them they cannot hear us. Yeah, yes. Yes, we can hear. Okay. Okay. Sorry. Okay. So see again, think about embedding like a map. So the world is three-dimensional while a map is two-dimensional. So what is it doing? It is embedding each point in a three-dimension to a point in two-dimension. Okay. And what is it maintaining? It is maintaining, see, it is typically maintaining what? That if in the three-dimension globe, America is nearer to Canada, then in the two-dimensional map, America will also be nearer to America. But you will see some aberrations in the map also. Okay. So say the size of Greenland, which is shown in the map, may not be exactly the size of Greenland. May not be the exactly size of Greenland. Uh, because it may be so that the size of Greenland you will see in the map is much bigger, while it is not, it is almost comparable to India, but it may not be as big as India. So there are some aberrations or some differences from the three-dimensional map to two-dimensional map, but many metrics which are which are actually applicable in three dimension are also applicable in two dimension. This is how the embedding evaluation can be done. That whether the embedding is you have a lower dimensional embedding. When you have a lower dimensional embedding, whether it is preserving the properties of higher dimensional embedding, and it cannot it cannot preserve all the properties, but the important properties which you require for your task are embedded or not. That's why we also tell it a contextual embedding, task specific embedding. So there are a lot of things which we say that okay, this embedding is for this task. For a different task, there can be a little bit different embedding. Okay, fine. Go ahead. Who gives weights? How are they determined? What is the importance of bias? See, bias is again a sort of regularization. If you think bias means it may have a little bit different things, but let us think bias as regularization. What is regularization doing? Regularization is basically telling, again I have told you, whatever is present now, that is not absolutely important. There may be something you are missing, and that's why I am giving you a regularization. And who give weights means this is the weights which are there. This is a parameter. Means if you think there is no weights or things, but if you maybe many of you may have heard that some llama has 8 billion parameters. Say Llama has 8 billion parameters, Llama has 70 billion parameters. Okay. So what are those? Those are the weights. Okay. And these weights are slowly optimized. So why this becomes difficult? Because you have so many weights to optimize. And that requires a lot of data to really train and optimize those weights. Okay. We adjust all weights after a, but how much does the network decide which layer needs bigger correction versus smaller? And can we please revisit the appropriation with math function explanation? Can Professor cover? Yeah, we can think about this, that we can cover. Just now it is not possible, but we can talk about gradient descent a little more in the next class if everybody thinks. And see, again, this is also interesting. Say when the weight is passing through various layers, okay, the top layer to bottom layer, will the weights be adjusted equally, or the top layers will get more weights adjustment than the bottom layer? I'm giving you this as an exercise. Think of a thought experiment that you have a multi-layer perceptron and you are back propagating the weights. Okay. And you are adjusting the weights. Which layers weights will be more adjusted? The top layer or the bottom layer, or everybody will have the same weight adjustment? We can talk about this in next class. I'm giving you this as a thought experiment. Go back and think. So this will take later. Okay, let us just regularization bias. We can talk about this, but let us take it later. I think this is not so important at this point. I will take this later. हाँ. So there are two things I just want to tell you, one small thing. See, there are something which are model parameters and something which we are giving as hyperparameters. Okay. So I have not talked about this. What is a model parameter and what's a model hyperparameter? Please go back and look into this. Then you will get a little bit of idea what the second, what is the last question. Okay. So you can just have a look. I will come back to it in more details. Okay.
Thank you, Professor Niloy, for the wonderful session. And Hello, everyone. While the session is over, in case if you have any queries, please stay on this call. Teaching assistants are available. Please feel free to ask all your academic queries over there, and TAs will be responding to them. And as sir mentioned, in the next session also, he will be covering few important queries. Once again, I would want to reiterate that we have discussion forum also available in case if you have any further queries after watching the recording. Okay, someone mentioned that I'm not audible. If you can just quickly mention in the chat box if I am audible to everyone, yes or no? Okay, great. So I'm audible loud and clear. Great. Thank you. Thank you so much, everyone. I'll just highlight it again if anyone missed what I mentioned just. Uh, Teaching assistants are available currently, and they will be addressing all your academic queries in the Q&A section. In case if you do not have any query, please feel free to drop off. In case if you want to ask more queries, just drop them in the Q&A section, and TAs will be responding to them promptly. Thank you, everyone.